Okay, I think everybody has come in. So I want to bid you good afternoon and welcome to the 9th Annual Shannon Memorial Lecture. For those of you who don't know, this endowed lectureship commemorates the achievements of Claude Shannon, the founder of the modern digital information age, through an annual lecture by a distinguished contributor to the field of information theory. The lectureship was conceived and initially endowed by Jack Wolf in tribute and gratitude to Claude Shannon, and as a means to promote interest in information theory. So it's a great pleasure to welcome our Shannon Memorial Lecturer, Professor Thomas M. Cover, who is the Kwoh-Ting Lead Professor of Engineering and Professor of Engineering, Electrical Engineering and Statistics at Stanford University. Tom has been an influential force in the field of information theory for almost 50 years. His more than 120 papers include seminal works in several areas, including network information theory, which includes his award-winning 1972 paper on broadcast channels, and also spanning all the way to information theory of investment portfolios and gambling, which is going to be the theme of his lecture today. Tom has received many awards, notably the Claude E. Shannon Award, which is the highest honor given by the IEEE Information Theory Society. And he is also a member of the National Academy of Engineering. He's a renowned teacher, and his book, Elements of Information Theory, has been a bestseller and continues to be more than 20 years after its first publication. And that book was co-authored with one of his PhD students, Joy Thomas. One other thing I'll note is that Tom has created a quite original course on the mathematics of sports at Stanford. And if you go to the website for the course, you'll notice that it has links to a variety of resources, including the ESPN homepage and BBC Sport. I think this is a course I would like to sign up for if I could, Tom. Tom has mentored more than 60 PhD students, many of whom have gone on to distinguished careers in information sciences and information technology. Interestingly, among them is Abbas El-Gamal, who is also a professor of electrical engineering at Stanford, who himself is the most recent recipient of the Claude E. Shannon Award. I'm not sure how many Shannon Award winners have academic children who also received the Shannon Award. So congratulations on that. Another of Tom's students is our very own Professor Young-Han Kim. And I would be willing to bet that Young-Han will one day receive the Shannon Award. But I will consult with you first, Tom, about the odds. And now Young-Han would like to say a few more words about our distinguished speaker, Tom.
Okay. Thanks a lot, Paul, for a wonderful pre-introduction of Professor Cover and very generously of myself. Good afternoon. This is a great pleasure and honor to introduce my dearest mentor, Professor Cover. At the event, the links 3 people I admire most in my field of information theory: Claude Shannon, Jack Wolf, and Tom Cover. Tom grew up in, could you switch this to the slides, please? It's cover.pdf.
Can you tell me which ones are your slides?
It's cover.pdf. That one. You have it there. So Tom grew up in San Bernardino as one of 4 brothers with 4 most popular names of the time: Tom, Bill, Chuck, and John. And Tom once told me that his high school days were like the movie American Graffiti, so it must have been pretty exciting. And he did his undergraduates at MIT studying physics. Then 2 things happened. First, during the summer of 1960, he read von Neumann and Morgenstern's book on game theory. And perhaps more importantly, he read a book by Shannon and Weaver on information theory. And these 2 fields stayed with him throughout his academic life. And another thing is he came back to sunny California and studied with Norm Abramson as his advisor. And as you all know, the rest is history. Tom has been making seminal and fundamental contributions in broad areas of information sciences. His thesis titled Geometrical and Statistical Properties of Linear Threshold Devices paved the way for the theory of learnability. His classical paper titled Behavior of Sequential Predictors of Binary Sequences solved the problem of universal prediction of binary sequences. And amusingly, back then, he was just starting, and he thought the paper was not good enough for a journal publication, so he stayed in the conference proceedings forever. And other important contributions include nearest neighbor pattern classification, learning with finite memory, each on its studying on its own field. And arguably, he is the best post-Shannon information theorist. As Paul mentioned, in 1972, he published his paper on broadcast channels, and this work opened the golden era of multi-user information theory, along with Oswald and Liao's multi-access channel and Slepian of distributed source coding. He made many fundamental contributions in information theory ever since then, and perhaps his crowning achievement is his textbook, Elements of Information Theory, which you all know popularized information theory as is now. And I just saw 2 people from the audience came to the podium and asked for autographs. He also contributed in complexity theory, physics of information, and mathematics of sports and games, as Paul just mentioned. And for example, he asked and answered questions like, do longer games favor the stronger player? Or are all sports equally exciting? And also, he gave the most intriguing answers to two-envelope paradox. Tom's passion for probability took the centuries-old field's most classical form, which is gambling. And whatever legend you hear about him and gambling, such as card counting at Las Vegas and being blacklisted, or bringing a mobile roulette gambling device to Reno and use that to game the game, and taking part in a high roller poker tables, which included the actor Jack Nicholson, or going across the San Francisco Bay to play some backgammon, or even devising a winning gambling system for Casino Mogul. And I can tell you these are all true. And Tom's passion for probability took the most academic form, and he went beyond merely experimenting as a player, but he distilled his passion in the subject into beautiful theory, as evidenced in gambling estimate of the entropy of English, compatibility of optimality of Huffman code, and logarithmic portfolio, sandwich proof of the Shannon-Macmillan-Bryman theorem, universal portfolio theory, and what we'll learn in today's lecture. Another important aspect of Tom's academic contribution is his student. Quoting a phrase by a Nobel laureate, Paul Samuelson, Kwoh generated 64 Poisson-distributed students over the past years, and there are more in the queue. So this list, while there is a dud like myself, it includes luminaries such as Peter Hart, as in Duda and Hart, Martin Hellman, as in Diffie and Hellman, Abbas El-Gamal, Paul just mentioned, Joey Thomas, as in Kwoh and Thomas, and Michael Tanner, as in Tanner and his graph. Just to give a glimpse of his mentoring style, here are some quotes from his student's thesis. So let me just read part of it. His ideas have shaped my thinking, my tastes, my philosophy. Here is another good one. Perhaps what separates Tom from most is in the gracious manner with which he treats all his students and the commitment he has for them. For that, I'm forever grateful. My advisor, Tom Kwoh, told me, if you want to sing, you can sing. Tom Kwoh told me how to sing, which I'll be forever grateful for. His personality is an unusual mix of both mathematical rigor and jazz-like spontaneity. He inspired me. So with all this, I'd like to welcome Professor Tom Kwoh to the podium.
Well, thank you. Can you hear? Thank you, Paul and Young Han, for that lavish introduction. I see, though, that that puts pressure on me, but nothing like the pressure Paul just put on Young Han to become the Claude Shannon lecturer in the near future. Before I begin, later on this afternoon will be remarks about Jack Wolf, who's recently passed, and I would like to add my own, that he was one of my dearest friends, he was a brilliant researcher, and he was one of the founders of network information theory. Now, today I would like to give the Shannon Memorial Lecture, and I'm very happy and proud to be asked to do so. I'm going to talk about Shannon and the St. Petersburg Paradox. Most of the talk will be about the St. Petersburg Paradox, but Shannon has had an eerie influence on the development of the approach to that subject, and it generated a tremendous backlash, of which I will tell you more. In 1956, Kelly, who was at Bell Labs just as Shannon was about to leave for MIT, noticed a curious relationship between gambling theory and information theory. And it goes like this. All right. Let me ask again. Can you hear back there? Good. Suppose we have horses 1 through M, and the probability that horse, say, I wins the race is P sub I, and fair odds on the race are M for 1, since there are M horses. And the bets, how much you bet on each of the horses, B1 through BM, are non-negative and sum to 1. It's the proportion of wealth you associate, which you gamble on each of the horses. Now, one of those horses will win. Say the ice horse, which case you get M times the amount bet on that ice horse, but you won't get any more. You could tear up the other tickets and throw them away. So S is a random variable. You start with $1 and you end up with S dollars. And the question is, what should your portfolio be? Notice that if you keep investing this way, that you get a product of these wealth factors, the factor by which your wealth grows each investment, and that can be written as e to the sum of the logs. Multiplying and dividing by n, we notice this quantity is the average of independent, identically distributed random variables, and it goes to its expected value. So you get that the product behaves like e to the expected value of log s. This is called the geometric mean, and it turns out that the other approaches to the St. Petersburg Paradox and other investment pretty much put emphasis on the expected value of the return. Well, the expected value comes up in the law of large numbers for sums, but for repeated investments, the appropriate law of large numbers is the law of large numbers for products, and you get the geometric mean instead of the arithmetic mean. And this is the source of tremendous controversy. Markowitz won the Nobel Prize for his work in 1956, in which he looks at the mean and the covariance of an investment. Again, perhaps not as appropriate as looking at the relevant quantities for repeated or reinvesting one's wealth. So Kelly did the following analysis. He maximized the expected log return, call that W, and then maximize it over B, call that W star, and you get that it's log M minus the entropy of the distribution P, where the optimal portfolio is precisely the probabilities the horses win. And one gets a nice formula that the doubling rate of wealth plus the entropy rate of the horse race is a constant, the log of the number of horses. Every bit of information you get by, then he looked at side information. Here's the contact with information theory, not that that's not already a contact. He says, suppose you have a horse race outcome V and a side information Y, like the jockey's weights or track conditions. Then there's a mutual information between V and Y. And it turns out the increase in the doubling rate of your wealth is precisely given by the mutual information of the horse race and the side information Y. Later, Barron and I generalized that to show that for a general stock market, delta W is less than or equal to that mutual information, with equality if and only if the stock market is a horse race. By the way, a horse race stock market is the worst thing you could conceive of. That's where you have IBM, Coca-Cola, et cetera, to invest in, and tomorrow you find out, IBM went up by a factor of 10, and all the others are 0. That's a horse race. Now, Shannon looked at, well, Shannon obviously, we don't know the relationship of Kelly's ideas and Shannon's. They were at AT&T Bell Labs at the same time, and Shannon, of course, was aware of that result. And in 1966, he gave a very famous lecture. He never published on the subject, but in that lecture, several hundred people showed up, and it overflowed the large room. They had assigned to it, and they had to go to the big auditorium to give the talk. And at that talk, he advocated investing in such a manner that you maximize the expected log wealth. That is, you maximize the growth rate of your wealth, the exponent in the growth rate. Now, Bryman had proved that if you maximize this growth rate for a horse race market, not a general market, that it minimizes the time for your wealth at time N to achieve some distant goal A. So that's where things stood. And however, in 1977, we have a paper by Paul Samuelson, the preeminent economist of the last 50 years, the winner of the first Nobel Prize in economics. And he stated, our analysis enables us to dispel a fallacy that has been borrowed into portfolio theory from information theory of the Shannon type. Sounds somewhat snarky, actually. If we didn't understand that he thought that maximizing the expected log was just maximizing another utility function, he spelled it out in 1979 with words of one syllable. The title of the paper is Why We Should Not Make Mean Log of Wealth Big, Though Years to Act Are Long. So we had occasion in 1986 when Shannon visited the Brighton ISIT meeting to ask Shannon, what caused this reaction on the part of Paul Samuelson? And Shannon expressed surprise. He says, during the early 60s, we used to meet at my house and then Paul Samuelson's house. We'd alternate, maybe someone else's house, to discuss questions of investment and economics. So it was total news to Shannon that, in fact, Samuelson had veered away from information theory of the Shannon type. And then, when Bell and I had something on competitive optimality, I'll say more about that, and when Ziemba became a passionate advocate of what he calls Kelly gambling, Samuelson fired off some letters of personal correspondence. Now, Young Han has already shown you one of these. This was sent in 1988. I'll blow it up here. And it says blah, 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 blah. And at the end it says, the majority of people don't use log W, but use a utility function of -1 over W. And this majority, which is vastly in the majority, as he says, he didn't say it redundantly, I did, but he said, you should not accept council from Latine, Kelly, Bryman, Robbins, Markowitz, Hackinson, Cover, and the PhDs who appear with Poisson probabilities every June. So this is in response to a paper that I had sent him a courtesy copy of. I never met him, and he never met me, and so on. And it finishes with a very playful but strong remark. Still, Barnum was right. Now, for those of you who don't know, Barnum of Barnum and Bailey Circus said, "A sucker is born every minute." So that's what we're up against here. If you are interested in maximizing the expected log, Samuelson will say that's wrong because it's just another utility function and it's not the right one. It doesn't capture human behavior. But we would say it's right, at least in the sense that there's a theorem about it. If you maximize expected log, your money will grow at the highest, exponentially fast at the highest possible rate. Now we come to the main subject here. Daniel Bernoulli, in 1738, became aware of the St. Petersburg Paradox. That's where you take $1, you give it to somebody, and you take $C and give it to somebody, and they give you back in return a random variable that takes on the value 2 with probability a half, 4 with probability a fourth, 8 with probability an eighth, and you can see that the expected value of the random variable given back to you is infinite. So you pay C, you receive X, and you're very happy because the expected value of X is infinite. Now, are you willing to pay any price C to receive X minus C? Well, as you can see up here, most of the probability is down low, and if the price you are asked to pay $1 million to play this game, common sense says no, don't play. Your $1 million will turn into $2 or 4 or 8 most of the time. But common sense also says that the expected value is infinite, and you don't maximize your path through life by passing up opportunities that have infinite expectation. So the answer should be yes. Some say no, but the expected value is infinite. Would you pay $1 million? The answer should be yes. But why, and what do we mean by yes? So I hope here to talk about a possible resolution of the St. Petersburg Paradox. But I'll just say right now, no one is going to accept anybody's resolution of this paradox. It's not because we don't become true believers when we go down a certain path. Samuelson down his, and Shannon and others, growth rate optimality down theirs. But somehow there's not a meeting of the minds here, and I don't expect there to be. So it would be foolhardy for anybody to say they have resolved the paradox. Nonetheless, I'm quite happy with what we'll be saying here. All right. So here are the previous resolutions of the paradox. Bernoulli, in his original paper where he talked about the paradox, said, you know, people count money by the number of digits of money. You know, he makes a six-figure salary or an eight-figure salary, and maybe you're indifferent to a 50-50 coming up with a nine-figure salary. So he advocated the use of the logarithm as a utility function. And he wanted to maximize that utility, and that's what his paper was all about. Now, the objection to this over the years has been this utility function is arbitrary. It tells, look, utility function theory came into being really with the work of von Neumann and Morgenstern, in which they wanted to analyze games in which you had one random circumstance or another. For example, would you rather have $100 or a 50-50 chance at $10 million or being boiled in oil? So being boiled in oil doesn't have a dollar value, so he advocated, Bernoulli did, and von Neumann and Morgenstern, really advocated assigning a real value to each of these outcomes. And the main theorem in utility theory is if you have a linear ordering of distributions, that is gambling preferences, then there's a utility function which, if you take the expected value, will induce the same ordering. Problem with that is you're demanding a lot of people when you ask them to come up with a linear ordering of gambles. There are a lot of people who get a circle going. A beats B, beats C, beats A. That's ruled out. So on. And second of all, you're being descriptive rather than prescriptive. You're trying to describe the idiosyncrasies of human behavior and then honoring it and maximizing it. Now, a particularly disgusting objection to the St. Petersburg Paradox are those people who say there isn't enough money in the world. In other words, you can't offer $1 zillion with probability 1 over a zillion because there isn't that much money in the world. And of course, they're right, but throwing a paradox out for certain kinds of primitive physical reasons, like counting the amount of money in the universe, doesn't seem like an aggressive intellectual approach. So I'll just throw that out. There isn't enough money in the world, but it's still an interesting paradox. Now, Feller entered the ball game, and he says, you know, the distribution of X, the St. Petersburg distribution, is not very good. That is, X minus C is not very good because you lose most of the time. But what if you add a lot of X's and pay a lot of C's? N times in particular. Now do you like that distribution? And the answer is yes, you like that distribution more. But my objection here is this isn't what's being offered. You're being offered one shot at the St. Petersburg game. And also, what if you don't have NC dollars, so you could play it this many times in parallel in space at a given time? And finally, if you take this argument to its conclusion, you see that you can get the expected value back out by repeating things, adding them up, and dividing by n, which is to say you can squeeze all the randomness out and retrieve the expected value. And that's not true. Try it in the stock market. If your expected return tomorrow is 1%, try to get that. If you invest, you'll get a random variable with mean 1.01. Now, Samuelson wrote 2 papers on the St. Petersburg Paradox, and he spent a good deal of time talking about utility theory, the correct utility function, and he argued strongly that the log utility didn't reflect human behavior. Now, just to throw a wrench in the works, just as soon as you say you had a growth rate optimal approach, you want to maximize the expected log, what if the expected log is infinite? Then every portfolio maximizes the gain. So the super St. Petersburg paradox, in which you get 2 to the 2 to the k dollars, minus 1, with probability 2 to the minus k, has an expected log which is infinite. Now we want to dispense with that too, and we'll introduce a way to do it. Okay, so here's the story. Gambling is trading one random variable for another. We have a $1 with probability 1. That's our first random variable. In return, we get 1 minus b, the proportion of wealth we keep in cash, plus bx over c. Remember, the entry fee is c, so c dollars buys you x. So $1 buys you x over c. All right? So this now becomes the growth factor of wealth. And B represents the proportion of all of your assets that you're willing to invest in the St. Petersburg game. And the geometric mean associated with that, yeah, it grows exponentially fast with exponent W. Now, if we maximize this over B, we do it by taking the derivative with respect to B, and we get this nice quantity. We set it equal to 0. Now this crosses 0 only once, as B ranges from 0 to 1. So, well, you can do it by approximation, or sometimes in closed form, but you can find the optimal portfolio B, the one that maximizes this. We'll call this equation star. Now let's see how the growth optimal portfolio B behaves as a function of the entry fee. So here's the entry fee, C along here, and here's the proportion of wealth you put in St. Pete. Well, for 2, since you always get your money back, put it all in. For 3, you put it all in. For 4, you only put in 30%. And by the time you get to an entry fee of 8, you really don't want it. You put 2% of your money in St. Petersburg. So that satisfies common sense. Yes, you want St. Petersburg at any price, but how much you want falls off spectacularly fast as the price gets even somewhat large. So let's look at the behavior of that. 2 to the W star is the effective, factor by which your money grows as a function of C. And for costs greater than 4, you don't grow much faster than just keeping it in cash, but you grow a little faster. All right? So let's look at what we're doing here. Cash is $1 with probability half, a fourth, an eighth, a 16th, etc. St. Pete is 2, 4, 8, $16 with probability half, a fourth, an eighth, a 16th, and so on. We're forming the mixture of these two random variables, B bar plus BX over C. And we see that we get this distribution, and here are the probabilities, and here are the payoffs. Let's look at it for a cost of 3. Cash is here. St. Pete over 3 is here. That's the payoff. And the mixture random variable is 2/3 with probability half, 4/3 with probability a fourth, and so on. We find the exponent is this, and the effective factor by which your money grows, if you're offered this opportunity at price 3, is 33% per gamble. Very exciting. Here I've just plotted what the gamble distribution looks like. Here's $1 straight across as we look at the index K, that is in the probability 2 to the minus K. So with probability half, we get this amount. With probability of fourth, we get this amount, etc. So that's the distribution. We're trading that distribution for this one. Looks like a good trade. Let's try entry fee 4. We do this. We divide by 4. We look at the optimal mixture, and now the optimal mixture is 38% St. Pete and 62% keep it in cash. And the resulting distribution is 0.85 with probability a half. Yeah, you've lost 15% of your net worth, but you get your money back with probability of fourth. You're up 30%, 1/8, up 90%, 1/16, and so on. And your growth rate of wealth is now 10% per gamble. And here's the distribution that you get instead of the flat one, which is cash only. So it satisfies the test of how it looks. Now let's look at C equals 8. Now we get the B star is 0.02. You only bet 2% in St. Petersburg. That's pretty modest. The results this distribution, 0.97. Oh, you might have lost 2% of your money, or 1.6% of your money, etc. And it stays flat for a while, then it takes off. But it didn't take off very fast, because now your growth rate of wealth is 0.4% per gamble. So actually, maximizing the expected log is not giving you answers that violate your common sense. I'd like to mention briefly something we notice in our analysis, and that's the role of 3 critical arithmeans. See, the arithmean is expected value x to the rth root thereof. When r is 2, that's root mean square. When it's 1, it's the mean. When it's 0, you use L'Hopital's rule. You find out that it's the geometric mean. And when r is 1, you get the harmonic mean, which is the reciprocal of the expected value of the reciprocal. What role do these play? Well, besides their coming up as the answers to the questions of addition and multiplication of independent random variables, we look over here, and the way it turns out is this. here's the mu1, the expected value of x. It's actually infinite for St. Pete. For anything to the left of x, anything higher than mu1, we don't want any of that random variable x. Its expected value just was not good. For anything lower than the harmonic mean, we want all of x. And strictly between the arithmetic mean and the harmonic mean, B star will go from 0 to 1. That is, this is the region in which we'll want some of our investment X, and it will be growth rate optimal. So that analysis is done here. You just take those derivatives, substitute in B star 1 and 0, and you get the results I just mentioned. Now, it turns out that when you have the right answer, it turns out to be the right answer to a lot of questions, different questions. Pi comes up as in geometry, it comes up in probability theory, normalizing for the Gaussian, comes up. It's the answer to a lot of questions. So we would expect that the portfolio that maximizes growth rate might also have some other properties that don't have anything to do with growth rate. So let's suppose you look at Sstar, the optimal portfolio, and S, what occurs when some other investor invests. We were able to show in 1980 that maximizing the expected log is equivalent to finding the random variable S star, which extremizes the ratio of S to S star. And as a result of that and Markov's inequality, you can show that the probability any other investor beats S star is less than a half. So consider the two-person zero-sum game. You and I invest in the stock market, IBM, et cetera, and one of us, we both know the distribution of tomorrow's prices. One of us uses B star, the growth rate optimal portfolio, and the other doesn't. Well, then the S star will win that game at least half the time. Now, can it win it more? No, because your opponent, player 2, can use S star as well. So, so this is the value of the game and the solution to the game. And notice no logarithms take place whatsoever in the formulation of the criterion. You're just trying to outperform your opponent. So now we have established that B star is not only growth rate optimal, but it's competitively optimal in one shot. So while you're on your way to growing money to infinity exponentially faster than anybody else, you have greater amount of money at least half the time than your opponent along the way, including the first step. Okay, now let's throw the wrench into the works. Let x be super exponential. Look at it, 2 probability of half. Takes on the value, it pays you back $8 with probability of 4th, 128 1/8, 32,000 with probability 1/16, and then it takes off from there. Do you want that? How much are you willing to pay for it? Well, if you look at it, for any positive portfolio B strictly between 0 and 1, your money will go exponentially to infinity. That is, it's insensitive. X is so big that your money will go to infinity exponentially fast. So it looks as if your solution and the problem are degenerate. But wait, if you live on a street of millionaires, it's nice to be a billionaire, because then you get your choice of houses and so on. In other words, what we're really interested in when we're both going off to infinity is having more money than anybody else. So we look at the ratio of the wealth from B to any other, say a half-half portfolio, which I have here. Any one will do in the denominator, and we wish to maximize that ratio. That defines a relative growth rate, and this relative growth rate has nice properties. It's finite even when the terms that comprise it are infinite. Because the ratio is finite. If I broke the log of the ratio into the sum of the logs, I get infinity minus infinity. That's where it would break apart. So we find this is finite. There's a triangle result. But when we find a portfolio that maximizes this spectacular investment opportunity, we find it satisfies the same equation, Sstar, as the one for the other. And that's because the denominator didn't depend on B. We're comparing it to, say, the half-half portfolio or any other fixed portfolio. So, in repeated plays, while you're both surging off super exponentially to infinity, the ratio of Sstar's wealth to S's wealth grows exponentially fast. So, in a world of inflation, you're winning. Now, let's see what the optimal portfolio looks like when offered super St. Pete. Now we see that it's no longer very conservative. Even for C equals 10, you want to put 30% in super St. Pete. By the way, for 4, you put in 100%. And for 20, you still put in 22%. When we figure it out for a cost 8, you put 42% in St. Pete. The optimal mixture, that is the random variable you're going to get in return. And I'll tell you, I can't tell you how many times I've thought of Jack and the Beanstalk, where his mother tells him to go to the market with a cow, and he comes back with 3 beans in his hand. So that would be a classic exchange, one random variable, the cow, for the other. And as we know from Jack and the Beanstalk, he made a good investment. Although his mother doesn't enter the story again, as far as I recall. So, here's how the profile of the outcome behaves when I invest log optimally. Notice I do lose money with probability of half. I get my money back with probability of fourth, and then it takes off with probability an eighth, and 1/16 is something up around 4,000 here. So now I'd like to make two sets of concluding remarks. First about the St. Petersburg Paradox, and then about the role of Samuelson and Claude Shannon and others in it. I believe this is a reasonably satisfying resolution of the paradox. You don't repeat it in space. Who gave you that right? That's not right. You instead allow yourself to buy a fraction of St. Pete or many shares of St. Pete, depending on your total wealth. And B is the proportion of that total wealth that you invest in St. Pete. The random variable that results is Sstar. And the nice thing about Sstar is not only is it growth rate optimal, but it's relatively growth rate optimal. That is, even when you blow up the problem with super St. Pete, you still get a sensible answer by looking at equation star. Also, you get competitive optimality in one-shot investment that should satisfy those people who don't like a horizon of infinity to justify their investment. The wealth of the log-optimal gambler is growing exponentially faster than the wealth of some other gambler. And the most satisfying is that Sstar, the random variable you get by mixing them optimally, passes the eyeball test. It's a reasonable distribution. If somebody just gave you these two distributions, you say, here's $1, and here's this distribution, you want it, you'd want it. And so the concluding thing for the St. Petersburg is there isn't a price that's too high, not even $1 million. But you want less and less of St. Petersburg as the price goes up. And that satisfies because that effectively says, yeah, $1 million is too much, at least for St. Pete. Maybe for super St. Pete, it isn't. So finally, let's talk about Samuelson and Shannon, so on. I can only speculate on what caused a parting of the ways of two people who respected each other and had meetings at each other's houses in the 60s. When Claude Shannon gave his talk in 1966, it caused a huge stir. There were many, many hundreds of people who attended that talk, and there was a buzz about it. And at that point, Samuelson might have been a little irritated. And this may have caused him to make these caustic remarks about information theory of the Shannon type, which sounds like a disease or something else, to make those remarks. But I will say what I've said here today supports the Shannon point of view of growth optimality. and supplements it with some other things like competitive optimality and its application to St. Petersburg Paradox and the super St. Petersburg Paradox. Thank you. Yeah.
So are there any questions for Professor Kwoh?
I'm not offering to gamble because there isn't enough money in the world.
Yeah, I think we have.
Yeah.
Is it interesting to look at the chance of ruin in this model? Because if you invest 30% of your wealth in Super St. Petersburg, there's still a chance that you're going to go broke after a certain number of plays, right?
Did you hear that?
He's asking about whether the prospect of ruin, that you might go broke.
No, the nice thing about proportional gambling is you never go broke because you're always left with a positive amount of money. If X is a non-negative random variable, and if you could mix X with cash, you can even allow X to take on the value of 0 or some number A with some probabilities. And then you'd find that you'd always want a little money in cash because you don't want to go broke. So, no, there'll be no ruin. However, I will say this. For some investment opportunities in which you're forced to invest, and these were not the ones I talked about, the growth rate W, even when maximized, might be negative, which means your money will go exponentially to 0. Never be 0, but it'll go exponentially to 0. And now, what makes you happy? You're going exponentially to 0 more slowly than everybody else.
How would the conclusion change if you allow short or margin?
Yeah, if you're allowed short selling or margin, well, I said for prices for costs less than the harmonic mean, you want all of St. Petersburg. Well, if you did short selling and margin, then the harmonic mean is the demarcation where you'd want to start buying on margin. You'd buy St. Pete on margin if somebody will loan you the money. Andy?
Is Super St. Petersburg like venture capital?
Well, the Super St. Pete, that's what the venture capitalists would like to tell you. Right, that this is too good an investment to pass up.
I have one more question.
Yeah.
So, how much do you charge to look at your investment portfolio? You don't have to respond.
If only I spend as much time on my own investments as I do on the theory of it.
Okay, all right. Let's thank Tom again. We always present our Shannon lecturer with a plaque.
Ah.
So if you want to come over here, you can show everybody your beautiful plaque. And a replica of this will be mounted in the lobby of CMU.
Thank you.
So thank you again, Tom, for a wonderful and enlightening talk. It's always nice, it's interesting to hear about these feuds between brilliant people and try to understand what the basis for it is. So there's one other thing we typically do in conjunction with the Shannon Memorial Lecture. This is a tradition that was initiated in 2008. And that has been the presentation of the Shannon Graduate Fellowship. So this is another endowed or endowment that was conceived and funded by Jack Wolf. And the intent was to recognize an outstanding graduate student who's working in the area of information theory. The recipient gets a nice framed certificate and also a supplementary stipend, which is academic lingo for some extra spending money. So this year I'm pleased to announce the recipient of this award, the 2011-2012 Graduate Student Fellow. And it is Hessam Madavafar, a student of Professor Alex Vardy, and I hope Hessam is here to receive, yes, his award. The nomination letter for Hessam showed that he has exhibited breadth, depth, and creativity in his research. It's been primarily in the area of algebraic coding theory. And for those of you in the know, he has looked at the theory of burst error correcting codes, and he's also spent some time looking at codes for wiretap channels. And most recently, he's been looking at codes for error correction in networks. So I would like to congratulate you, Hessam, and call your advisor up if he's willing to make the trip, Alex Vardy. Congratulations. Congratulations, Alex. So we have a plaque here. Go on over. And this will be probably mounted in Hessam's office as opposed to the similar lobby, but nevertheless, congratulations. And we also have the envelope here, which that's the important. This is the important one, but it contains an IOU at this point. I guarantee it will be redeemed, absolutely.
Move forward to the light, if you could. Into the light. Thank you.
Okay, now, at this point, we were thinking of taking a 5-minute break. Is there a vote for a 5-minute break, or shall we just carry on? Carry on, okay. So the Shannon Memorial Lecture and the Shannon Graduate Fellowship in a very real way represent part of the legacy of Jack Wolf at UCSD. These are gifts that he gave to the entire community, and they're gifts that keep on giving. Can you hear me still with this? No. How about now? No. Now? Okay. We'll revert to Plan B. Okay. So now we have the wonderful opportunity to show our appreciation for these and the other things that Jack gave us. Last February, unbeknownst to Jack, a campaign was launched to establish an endowment of a chair in his name. And this campaign had the enthusiastic support of Jack's family, the Dean of the Jacobs School of Engineering, and the UCSD Foundation. So with help from Lisa French, who is the Senior Director of Development in the Jacobs School, and I think Lisa is right up there, the campaign got off to truly an amazing start when Dr. Andrew Viterbi, who was a close friend and colleague of Jack's for over 50 years and was well known to many, if not all of you, provided what is really an extraordinarily generous lead gift in the form of a challenge grant. And now, thanks to contributions from over 40 colleagues, students, friends, and foundations, the gifts and the pledges have far surpassed the level required to establish the chair. So the Jack Kyle Wolf Endowed Chair in Electrical Engineering will become a reality. And it will provide a lasting tribute to Jack, and it will support the efforts of the university to sustain excellence in the field of electrical engineering that he cared so much for. Now, we have several people here to offer remarks. Now, let me see if there we go. Thank you. We're very pleased to welcome 3 representatives of the campus. The first is Dave Miller, who is the Associate Vice Chancellor for Academic Planning and Resources and a Professor Emeritus of Mechanical and Aerospace Engineering. Charles Tu, who's an Associate Dean of the Jacobs School and Professor of Electrical Engineering. And Professor Shia Feynman, who is the Chair of the ECE Department. We're also delighted to have Dr. Viterbi and his wife Ernie here to celebrate the success of the campaign with us, and to have Dr. Viterbi make a presentation to Jack's wife Toby and other members of the Wolf family who are here today, which includes his daughter Sarah, her husband Charles, his daughter Jill, I think, is here, and his son Joe. And then finally, on behalf of all of the members of the Wolf Pack, past and present, Eitan Yacobi and Sehan Karakulak and Marco Papaleo and Aravind Iyengar will present an original and entertaining salute to Jack. So with that, I'd like to turn over the mic to Dave Miller.
Guess you just have to put up with administrators and things like this. But it's really a pleasure to be here. I've known Jack since he arrived, and I'm going to miss him a lot. I do want to thank, on behalf of the campus leadership, all of those who worked so hard and made contributions to the successful fundraising campaign to establish the Jack Wolf Endowed Chair. These kind of things are extremely important to the campus. They leave a legacy not only to honor Jack himself as a person, but to honor the quality of the institution UCSD. These have become, chairs have become really important mechanisms to honor our most distinguished faculty, but especially more and more I've seen in the last few years, they're extremely important to recruiting and retaining the highest quality faculty. Just every year it seems to make a difference in one particular retention or recruitment. And of course, Jack came here as one of the first 4 endowed chairs in the Center for Magnetic Recording and held the Rice Professorship. And he added to that legacy of that honor with all of these wonderful, brilliant things he did and got acknowledged for. I would like to point out one thing that I think should be on that list. In the year 2000, Jack was given the campus-wide Distinguished Teaching Award for teaching at the undergraduate level. And at the same year, he received the department's Electrical Engineering Graduate Teaching Award. And I think that speaks to the quality of Jack as a colleague and a faculty member, probably not as much as all of this, because this is a gift he gives to all of us as scientists and colleagues and impact. But he was dedicated to being a faculty member in those kind of standards in teaching and mentoring graduate students. And I remember when he got that award, I was still in the administration, and I said, I can't believe Jack Wolf got this award. He teaches these things like communication theory. And I remember looking it up, 154, ECE 154. How can anybody get a 100% teacher rating in a course that difficult in communication theory? It's really not easy to do. These are undergraduates, and they love to point fingers at professors, and of course, they're never responsible for their poor behavior, but Jack he always got something like 95 to 100% student ratings. And of course, in the graduate students and mentoring, he was really great. So the legacy of quality is very important to us on the campus, and I, again, want to thank you. I also want to say that I appreciate the fact that this chair is named broadly in terms of a chair in electrical engineering. I also think that speaks of a nature of Jack in terms of his breadth, and I always got a kick out of that statement that was attributed to him, that when he came here to take the chair in magnetic recording research, he said he didn't know anything about magnetic recording. But he came here, and of course, when you have a high-quality, brilliant person, their work is applicable to many, many areas. I think it's a good principle for us to remind ourselves as we're recruiting that quality is the thing that overrides everything else, because they'll move into important fields and make contributions to many things. So again, on behalf of the leadership, I really want to thank all of those who worked in the contributions to make this a successful fundraising campaign to establish this chair. Thank you very much.
Yeah, hi, good afternoon. It is an honor for me to speak on behalf of the Jacobs School of Engineering. Dean Frieder Seibli is away on travel, so he sends his regrets for not being able to be here today. We all grieve the loss of our dear friend and colleague, Jack Wolf. In his memorial service, we celebrated his life as a human being, but today we are celebrating his legacy as a faculty member, as Paul and David pointed out. So this endowed chair will allow us to remember him and his many significant contributions. And so it is fitting that this endowed chair is in the Jacobs School of Engineering, because as you have seen here, Jack was recruited to the Department of Electrical Engineering and Computer Science 27 years ago. And I've known him for 23 years, and he was always an active and contributing member of the department. And so he was a member of the Faculty Advisory Council for several chairs, including me. And I always value his common sense advice. So endowed chair, as mentioned, is a tool for recruiting and retaining outstanding faculty members. And indeed, Jack was indeed, the university used the chair to recruit him to the university. So, and as mentioned, we have already exceeded the minimum endowment requirement for endowment, and far exceeded. And so we are indeed very fortunate. So today is a happy occasion. So the Jacobs School is thankful to Jack for many years of contributions, and also to his family, friends, and colleagues for their generous donations to this chair. So in memory of Jack, and so that it's in perpetuity. So thank you. Yeah.
Good afternoon. I'm Shia Feynman from ECE, and I'm fresh on the job, so I'm not that experienced giving speeches, so I usually use a couple of bullets. So I wanted to share with you a couple of thoughts that I had in respect with the endowed chair on Jack's name. Jack was profound and proud to be electrical engineer and helped to shape up the ECE department during the last 20 plus years. In many of the faculty we hired, we have some mark of Jack. He helped to establish a very close relation with industry and academia, locally, nationally, and internationally. The establishment of Jack Wolf Endowed Chair in ECE is a tremendous tribute to his accomplishments by his friends, students, colleagues, and family. Thank you, all contributors, very much. We all know that we are experiencing difficult times in UC and UCSD as one of the campuses, and it is very challenging to retain and recruit new faculty. The Jack Wolf Chair is of huge help to continue keeping ECE at UCSD as one of the top schools in the world. We will use Jack Wolf's chair in ECE department either for retention, recognition, or hiring new outstanding faculty in ECE. So far, we got a go-ahead for 2 new positions from the Jacobs School of Engineering, and we will follow our past tradition to look for the best candidate. That's what we actually were always challenged by Jack. Since Paul Siegel is chair of ECE recruiting committee for 2011-2012, I think he will make an excellent candidate to chair the ad hoc for Jack Wolf's Endowed Chair committee. So we will ask him to consider chairing this additional committee. For the future, we want to continue find ways to strengthen the relation between ECE and our friends in industry, academia, and families. Thank you very much.
I have to say, I enjoy spending time with Shia very much, but I've learned that these days, since he became chair, every time I see him after our meeting, I have something else that I have to do.
Just like to make a couple of remarks before I hand over the plaque. Jack Wolf was my closest friend, and I dare say there are probably a number of people in this room and outside this room that can say the same thing. And this is attested to the fact that the campaign went so swiftly and so successfully. I would like to put in context the chairs, the endowed chairs, and in particular Jack's endowed chair that he held for some 27 years, the Rice Chair. When Jack came, the Center for Magnetic Recording Research was young. It had been just established through the largesse of a number of magnetic recording research companies. And among their offerings, which included, I think, the building, was also 4 endowed chairs, and Jack was offered one of them. Now, inasmuch as he claimed he didn't know anything about magnetic recording, that was an exaggeration, but what he did know a lot about, of course, was communication and information theory, which he brought to the magnetic recording community and really revolutionized the way they do things. Along the way, to have an endowed chair that just says CMRR is not that exciting, and he and I discussed what he really should name it, and he came up with the idea of naming it for the pioneer who had really taught electrical engineers and communication engineers about random processes, writing in 1944 a seminal paper in the BSTJ, Bell System Technical Journal, titled something like Mathematical Theory of Noise. Steve Rice retired after 44 years at Bell Labs and came to San Diego and was very active at UCSD, mentoring both young faculty and graduate students. He was much beloved here. So it was a logical choice. Of course, The administration didn't necessarily see it that way, and it took probably a year of back and forth. Finally, Jack decided he'd just call himself the Stephen O. Rice Professor, and nobody objected. So this time around, I trust that it's going to go much smoother. And I trust that we'll, under the leadership of the very capable faculty here, that the right person will be selected for that chair. Now it is my distinct pleasure and honor to present Mrs. Toby Wolf, who we've all spoken many times as how she was the alter ego to Jack for so many years, with this plaque. Toby. Thank you.
I'm the Toby of Toby and Jack, or Jack and Toby, whatever you call it. I really want to say thank you for everybody that has come today, from the Princeton co-worker of Jack and room with him, Gene Wong, to our landlord in Hawaii, Shu Lin from Davis, to some people from USC, the Viterbi School of Engineering there, and to people from Israel, to people from everywhere. All of his students that are here are beloved by Jack and by myself. There are a few people I have to thank specially, one of which is standing right next to me. Jack met him 50 some odd years ago. Jack was in the Air Force and was the person who people went to for grants. They wrote their proposals and they went to him for money. Guess who came? And many others. And he met the most remarkable people that way. It was an interesting period in our life. I'm glad it lasted only 3 years. He learned, though, at that point that he loved to teach. Syracuse University was right near Romare Development, and nobody would drive there in the snow during the winter. And so he was asked by Syracuse to please teach a course on the campus of RADC. He would go into the bathroom, change from his Air Force uniform into his regular clothes, then at the end of class, go back, change into his uniform, and go back to work for the Air Force. This was the beginning of his teaching. He loved it. He never stopped loving it. A funny story that I have to tell you about UMass. He had a 2-year commitment to be an administrator. Now, if you knew Jack, you knew he hated that job. And at the end of 2 years, he was asked by the president, the chancellor, I should say, of the university, to have 2 choices. You either take the deanship or 3 more years of the chairman. He came back home and he said, Tobe, what do I do? I can't stand this job. I said, quit. He can't fire you, you have tenure. So he went in the next day and he said, I quit. I don't want to be chairman. I don't want to be dean. That's it. I'm going to teach. And that's what he did for the rest of his life and was extremely happy doing it. The two other people I really want to thank. One of them is not here today, Roberto Padovani. He was a student at UMass. He came out to Linkabit when Andy was at Linkabit, and then he went to Qualcomm. And like Andy, he became Jack's boss. All right, so now he has two people that he's dealt with for a long, long time that are his boss. The third one is sitting right down there, Paul Siegel. He came on sabbatical and came back again to stay for good. And what did he become? Jack's boss. Very, very happy to be working for people he loved, who he respected. And I thank you all for making this possible. I'd like to introduce my son-in-law. And now, how many people can say they love their son-in-laws? But I do. And he must have loved Tom's talk because he's in the money market. Come on up, Julie. Say something about your father-in-law.
Thanks for the notice. I know Jack would be overwhelmed and quite a little humbled right now. Since he passed away a few months ago, the showing of support from his friends, his students, his colleagues has been something above and beyond anything anyone in the family could reasonably expect. We miss him. We think of him all the time, but with lots of fond memories, and this will be great. I hope this chair goes to somebody who loves teaching as much as Jack does, because it'll be a fitting tribute to him. Thank you.
Oh. This is Sarah, our daughter, who is an engineer, but then went into the money market again. Say something.
I just want to thank everyone for coming. It is wonderful.
Okay, well, I want to thank all of the speakers and all of the donors and all of you for coming. I also want to thank Iris Villanueva, who was the flower
Iris and Betty.
girl.
Whoa. There.
Iris, and also Sammy Romanin, from Cal IT2. I'm not sure if she's here, but the two of them have really done a tremendous amount in organizing all of the events today. Now it's time to go out and enjoy the reception in the foyer. And, oh no, excuse me. My students will kill me if I forget that. We're not quite ready for the reception, I'm sorry. Several of the students that I mentioned earlier would like to give their tribute to Jack, and I think you'll enjoy it very much. They've put a lot of work into it, so you guys want to come up here?
Hi, good evening, everyone. My name is Arvind, and the four of us here, there's Ehan, Marco, and Ethan, have put together something small, and here goes. We call ourselves, we think we're part of both the wolf pack as well as the flock of seagulls. The wolf pack, as you can imagine, was the group of students working with Professor Wolf, and the flock of seagulls was obviously those who worked with Paul Siegel. Um, so, as has been mentioned already here, Professor Wolf was a great teacher, and a clear indication of that is perhaps obtained when you, if you had seen his classes, which were scheduled at 7:30 in the morning. No graduate student wants to get up that early, but despite that, all of his classes were always full. And personally, I don't really remember seeing 7:30 in the morning after I stopped going to his classes at the end of the quarter. So for 4 years now, that's been the last time I really remember getting up early in the morning. He loved teaching, and you could see it. We students who worked with him, we got to see it quite a few times. I remember this one time when CMRR was having an exhibit at the San Diego Science Festival. This was about 2 years ago, and we had an exhibit on magnetic recording and hard disks and things like that. So I remember Professor Wolf he himself at home has a nice collection of electronic equipments from the past, and I believe his favorite was a gramophone. So I remember talking to him for half an hour on how it worked, and he was really enthused in teaching, and you could see it if you interacted with him. He liked to recollect how he accidentally ended up teaching, as Toby mentioned, and how he came to love it. Apart from teaching, he's also a great mentor. Always had good sound advice, not just technically, but also on how to deal with other things as well. So he started teaching at Syracuse University, but I think he had his first PhD students at New York University starting from 1965. I think that's when they graduated, so perhaps a few years before then. He was at NYU for 2 years, where he had 3 students. Yeah, and then moved to the Polytechnic Institute, New York University, where he was for 5 years. And one of his first students there at the Polytechnic Institute, Professor Lawrence Milstein, is now a professor here. And I was also taking classes which were taught by Jack Wolf and Larry Milstein at the same time. So it was interesting to learn at a later time that Professor Milstein was also Professor Wolf's student. So I'll quickly run through the list of his PhD students. So this is still in the Polytechnic Institute of New York, going into the 70s now. So he was there until 1974, I believe, when he moved to University of Massachusetts at Amherst. And again, at University of Massachusetts, he was for around 10 years, and he came to University of California here in sometime around 84, is that right? And this is around the time when I was born, so so he has been he has been doing this for quite some time. So it's really amazing to work with someone who's been in this area for a long time and knows everything inside out. So 27 years at UCSD, he had a lot of students, and I think the total comes out to something like 60 PhD students. Yeah, and a lot of visiting scholars and students as well. Now, his students have obviously gone on to excel in their careers. And they've been successful engineers, technocrats. Some of them have been very successful entrepreneurs, as well as some have been researchers and faculty members at various universities. So we try to trace back where the wolf pack is now, and we have just made a collage of all the logos of places where they are now. And as you can imagine, it's obvious that a lot of the companies in the semiconductor industry have benefited from Jack's students. So there is Linkomedia, LSI, Western Digital, SDEC, Marvell in the storage area. And then there is Qualcomm, Broadcom, Texas Instruments, Smart Modular Technologies, and a bunch of other companies in communication and general semiconductor industry. And there's also universities like UCSD, UC Berkeley, NYU Polytechnic Institute, UC Davis, the Bar Ilan University in Israel. And I think the logo on the right central portion is the Chinese Central University in Taiwan. So Jack's students have gone on to various places and have been influential. And also, we figured out that a couple of them have diversified, moved away from engineering, and are now practicing lawyers. So his influence through his students has been immense. There are a few of his students here, members of Wolf Pack. If you can stand up, that'll be great. So, yeah, we thought we should give each other a round of applause for sharing the experience with us over. Thanks for coming here. It's now over to Ethan, who will continue.
Thank you, Arvind, and good evening, everyone. I'm Ethan, I'm one of Jack Wolf's students. And maybe one thing, if someone ever asks you what the difference between something that you can count and something that you cannot count, then maybe PhD students you can count. We have like about 60. But what happens if someone asks you how many papers Jack has? So I can guarantee you, you cannot count. But as part of being a Jack Wolf student, we are really ambitious. So we did try to count them, and this is what we got. So, you know, we can go one by one, but let's see how many slides we can actually come up with. So it actually goes, and this is, you know, from the 60s and the 70s. And I guess you have to be patient over here. So it takes some time after all. And maybe some of them we can point out. So first of all, we have the first paper by Sletter and Wolf, who received the theory group, Information Theory Group Award. This is from 73. And we have really another nice paper from 78. This is number 38 over here. So going more, it wasn't, gotta say, very easy to get all of them. So, but we did try to do a good job. Another one which we wanted to mention here is the one with Andrew Viterbi is here, and Efif Zehavi and Roberto Padovani. This is from 89. And again, it really takes some time. And if you thought it was over at this point, then I'm sorry, like it's gonna take some more. Okay, and here is a really nice one also. This is from 92, who also received the IEEE Communication Society Leonard Abraham Prize Paper Award. This is with Brian Marcos and Paul Siegel. So again, going on, and another one, this is from the 50th anniversary issue for the IEEE Information Theory. And again, it wasn't really easy. Maybe it's another project for another graduate student to do a PhD on all of Jack's papers. I hope it's going to finish in 5 years. And so we tried to get all of them. And we thought that at this point it might be like too much. So we hope that we're almost done here. So I promise. But so we come up with some of like the last ones over here, and again it's hard to go one by one. And I'll stop over here because basically we could even continue more with even the patents and some other papers. But I guess you get the idea, and we also out of space with all of these dots over there, so it was a good point to stop here. So maybe finish up, and we stole this slide from Jack's presentations, and I guess it's one of his favorite ones, of the increase in the areal density in hard disk. And let's see how that goes along with Jack's career. And when you think about it this way, then 1956 we had the first hard disk, the Remac one. Not surprisingly, Jack finishes undergrad in the same year. This is from UPenn. And in 1960 he got his PhD from Princeton. We talk about his career in terms of institutions. Then he spent 2 years in NYU, and then it was about 7 years in Polytechnic in Brooklyn, UMass for another 11 years, and then in '84 he joined the UCSD CMR. And really one of the nice things about this plot over here, that you can see that there is an, I think I can use this one. Oh yeah. So over here you can see that there is an increase in the areal density of the hard disk. So does anyone have any idea what the reason for this increase is? Or if someone ever asked Jack what the reason for this jump in the slope here, any guesses? Well, if you ask Jack, it's very simple. And I stole this one from his slide. Then Jack Wolf arrives to the CMR in 1984. And I really stole it from his slide. And okay, so going on, let's see the distinguished awards, and you can also see the list in the papers that you have over there. So the 1975, we have this paper award for the Slepp and Wolf famous paper. And then in 1990, he won the Armstrong Achievement Award. Then 93, it was the Communication Society Leonard Abraham Prize Paper Award with Brian Marcus and Paul Samuelson. In 93, was also elected to the National Academy of Engineering. 98, he won the IEEE Koji Kobayashi Computers and Communications Award. And 2000, he won the UCSD Distinguished Teaching Award, which was mentioned before. Then 2001, he won the Claude Shannon Award. 2004, he won the IEEE Richard Hamming Medal. And if you can see over here, there is a slowdown in this increase here. So I guess the hardest skill really couldn't keep up with Jack's career, because from this year, you can just see many more awards. So 2005, he was elected to the American Academy of Arts and Sciences. 2006, it was the Robert E. Arnold Award from UPenn. 2007, so it's like every year you have something. 2007, it's the Aaron Weiner Distinguished Service Award. And very recently, it was the National Academy of Sciences. And just this month, we spent time with the Marconi Society Prize Award, which was about a week and a half ago. And today, it's actually, we're happy to announce the Jack L. Wolf Chair in Electrical Engineering. So with that, we'll finish here. And again, we'll thank everyone.
That was great. Thank you. Okay, so now I can really thank all of the speakers and all of the donors, and thanks to all of you for coming. I'll just repeat my thanks to Iris Villanueva and Semi Romanin, and please enjoy the reception in the foyer. And for those of you attending the dinner, it's been relocated to the CMRR auditorium, and there will be people outside who can help direct you to that location. Okay, thank you all very much.